All right. So basically, once we created the PN junction, we plotted the IV characteristic for a diode, and we showed that this is how diode behaves when we bias it. So this is the negative voltage minus V, sorry, not D, that's positive voltage, and that is I in milliamp. Incidentally, this I, which is minus I, is in microamp. So the amount of I that you see here is very, very, very small. This I is very, very small, is in microamp. So if I was to plot it nicely again, let me just see if I can do this. Okay, that's minus B, minus I plus V, this in microamp, this in milliamp, and these are in volts. And that is what diode looks like. So when we say forward bias, that connecting it this way, this is called forward bias. Which tells me this kind of biasing is for that part. And if we bias diode this way, that is for this part. Okay. Right. Okay. Since this diode can operate this way, and since on reverse it can actually, we can apply voltage and it can go so far and then suddenly break. Okay, we can manufacture a diode which we call Zener diode, a manufacturer specific design diode called Zener diode, that when we reverse bias Zener diode, we have specifically designed a structure that we reverse bias and we use it in that reverse direction, reverse biasing, and that when it wants to break, it does break the current. That means the current suddenly starts flowing after certain voltage, but then it can be reused. This diode will not be destroyed. It can be reused, and that is called Zener diode. So Zener diode is an ordinary diode that if I use it in forward bias, potentially it should work like ordinary diode. But it has specifically been manufactured with some provisions that when I reverse bias it, it will break it. That by breaking, I mean that it will have, the current will flow at a specific voltage called knee voltage or breakdown voltage. So all Zener diodes have breakdown voltage, and it is written breakdown voltage. So when we go to buy a Zener diode, we must specify what breakdown voltage do we need, what knee voltage do we need. We can buy Zener diode with breakdown voltage as much as 1.2 volt, for example, 4.7 volt, 9 volt, 18 volt, all kinds of voltages. We can buy Zener diodes at all kinds of voltages that they are available in the market. Right? So how do we use these forward diodes in a circuit, which we will go in a minute. We will continue that. But then before I go, so a diode. Now forget the Zener diode. The Zener diode is only for reverse biasing. We are talking about the ordinary PN junction diode. So as you can see that when we bias it forward, bias like this, VD, and there will be a current flow through this diode called ID. If we bias it this way, then when we apply positive voltage, this diode will conduct, and a current will flow. The current will flow like this. A current will flow like this through the diode. I, this is current I, will flow through this diode. But then, as soon as this voltage is reversed, if this voltage is, for some reason, same diode, this ID, this is VD, then this current I will be 0. Here I is a nominal value, say alpha. Here is 0. We won't have any current flow through the diode if it's reverse biased. Based on what we just discussed, based on what we just said. We said that when we applied forward bias, there will be current. But when we apply reverse bias, there is no current. So because of this, this is the conclusion we draw. I am going to face you all, and I'm going to ask, does everybody understand that? That a diode, when it's forward biased, that is current going positive, the diode will conduct. But when it's reverse biased, that is the polarity changes, there is no current flowing through the circuit. Arthur, are you good with that? Good. Eric? Fantastic. And the rest of you, I'm sure, because obviously we can very easily say, no, I'm not sure. Please stop me if that's the case. So I'm just taking it as everybody's good. Now, because of this property, because when diode is, the voltage applied to it is positive, it will conduct. When the voltage goes negative, it will not conduct. We find a fantastic application for that. We have a very important application for that very behavior. Because if we look at the mains that is coming to our homes, the voltage varies like this. The voltage that we receive in our homes is like this. It goes positive, and then it goes negative. And then again, it goes positive, and it goes negative. It goes positive, and it goes negative. Okay, why don't we apply that voltage to our diode? How do we do this? If we, for example, get a transformer, apply 120 volt AC there. And this is, for example, 10:1 ratio for this transformer. We're going to have 12 volt AC there, right? Do you agree? Right. Now, I'm going to put a diode there. And then I will put a load, whatever that load may be, just a piece of resistor would do for now. Let's see what happens. So when that point goes positive, when it's positive, when it starts from there, all the way there and all the way there, the same I can see there. Why? Because that voltage is positive, and this diode will conduct, and there will be current I, and this I through this resistor will give me a voltage with respect to ground. If I can flow a current through a resistor, there will be a volt developed across it. And that is what I measure there. Okay, so the voltage which I measure there, I'm going to measure voltage there. Now, of course, there's going to be a minutely less, something less, but nevertheless, there will be voltage there. But then, when this voltage goes negative, obviously this diode will not conduct. There will be zero I, and if it's zero I, there is zero voltage. So, oops. I am going to see what the voltage that I saw initially. Now I see 0 volt. Then so I started here, I went all the way there and there. I could see exactly that. Then when the voltage was negative, I didn't see any voltage. Then there is voltage goes positive. I can see voltage there again. And then it will just keep on repeating. This is exactly what I can see in the lab. I can actually demonstrate this. I can measure this, and I can see that to be the case. This is called half wave rectification or rectifier. This is this circuit is called half wave rectifier. Right. But it's a shame. It's a shame because I'm applying a full all that positive, negative voltage, and I'm not receiving the same amount of power. Some power is lost. So why don't I do something different? How about taking two diodes so that I will be able to catch the same. Okay, before I go into two diodes, let me just come back and tell you if everybody understood what I said. Is everybody happy with the half-wave rectification?
Happy.
Very good. So that with one diode, I can get only the positive excursion, only the positive side. For the negative, I get zero. I get no voltage. Right. When I use this kind of transformer, that is the diode that I had before. Then I'm going to use a center tap transformer. And I am going to put another diode there. And now I am going to bring out, how do I do this? How do I do this? I forgot. Where do I put the load? Okay. Oh dear, how do I do the load? Let me bring the, I forgot how to. Yeah.
The sensor tab, just a quick question. It'd be 6 volts, right? It'd just be half the voltage.
Oh no, it's not like that. It's much less actually. It's about 4.9.
Oh, okay, about 4.9.
Yeah, because we don't forget we lose 0.7 of a volt.
Yeah. Oh, okay. Yeah, I remember that.
Because there is a PowerPoint at the end of, I think, PowerPoint 1, which I've gone into giving you the mathematical calculation of what voltage do you actually get with one diode.
Yeah, that's actually what I was going to ask next, if you had an equation like that where it actually values.
Please refer to the end of PowerPoint 1.
Okay.
In fact, yeah, it'll tell you all that.
Thank you.
But anyway, with the center tap transformer, I don't want to know. Center tap transformer is not practical. We don't get center tap transformers anyway. So I'm not going to look up anything. So with two diodes, I can get the full rectification. But I'm just going to skip that. You can always look it up. But what we do use is a bridge rectifier.
Yeah.
So let me just go to bridge rectifier because we don't do center tap anyway. So I don't like this. I forgot how we connected the load, but then because okay, so I'm going to use the actual transformer that I used before, just like this, and now I am going to use 4 diodes. Just like that. And I'm going to connect my load there. RL. Now look at this. Remember when I said, okay, that is what's going to be applied. So the same obviously will be here because it's only a transformer. So there will be the same voltage applying there, only with smaller amount. So if the ratio is 10 to 1, and if this is, for example, 120 volt, this 120 volt is RMS value, but the peak-to-peak value of this, peak-to-peak is 100, it's 150, forget all these values. I think peak-to-peak is about 300 volts. 300, actually 120 times root 2. 120 times root 2, which is, root 2 is 1.4, right? So 100 and, let's just quickly tell you. 120 times 1.4 is 168. That's the peak. And then times 2, that is 336. That would be, oh, it's not 1.4, is it? Yeah, 1. Root 2 is 1.4, is it not? What is 2? 1.4, yeah. So the peak is 100 and anyway, I think the peak to peak is 300 and something voltage. Let me make sure. Am I confusing anybody? Are we good?
I'm a little confused. Just to make sure. So the peak to peak is just, you know, going from peak to peak, right? So yeah. Like 340 roughly, or no, 180 times 2. Never mind.
Yeah. Am I right or wrong?
Oh wait, yeah, 170 times 2. So like 340. Yeah.
So the RMS value times root 2 would give me the peak, and the peak twice that would be peak to peak. So so anyway, so this voltage, okay, if the peak to peak was 360 volt, divided by, that is 36 volt. That here the peak to peak is 36 volt. That is 10 times shorter, 10 times less. Okay, now this voltage, when it's positive, this diode will begin to conduct. A current will flow. This current I, which flows there, when it arrives this junction, it cannot go that way. It cannot go because this is reverse bias. This would be reverse bias. So the current will only come this way. That would be I. And then how is the circuit closed? Circuit starts from one end, must end in the other end. So the I will come through this resistor. It'll go that way. It will go that way. It will go there. And then it will go there. And it will go there. And it will arrive here. So the voltage which starts there will end up there. The voltage starts there, ends up there. That's a full circuit. So that would be I. Then when this goes negative, you see how the voltage, we so far discussed it when it was positive. When it goes negative, when it's negative, that voltage, this diode will not conduct because that's negative. But this diode will conduct because this is negative voltage, negative there, that must be positive. So this is like forward bias when that is negative. So the current will go that way this time. The current will arrive here, and it cannot go there because this diode won't conduct. It will go that way, and it will go through the load and there and there and back in there. Now this drawing, I have got it on the PowerPoint one. You can go and look it up again. So the direction of current on the first one is that way, through the load, there, there. And the other one is that way, through the load, and that way, and that way. So then the output, so if we now have this, if we have this as the input voltage, that's input. If we plot the output, we will have there. We will also have this. We will have this. We will have this. We will have this. And this is called full wave. That one, the previous one was half wave. This is full wave. So this is DC now. Why is it DC? Because the average of this was 0. The average of this is 0. How much we have, the average means the area under the curve. So that area under the curve and this area under the curve cancel each other. That area under the curve with this area on the curve cancel each other. So the average of this is 0. But the average of this and the average of this and the average of this is not 0, is it? So we have a nominal value here. So the average, which is the DC value, if we actually measure it, it'll be something like this. Means this peak divide by pi. But don't worry about this. The calculation I've given it you at the end of the PowerPoint. It's just that for you to see that, in fact, this is the DC value, but very, very bad DC. In fact, it's a very alternating DC. But the fact that it's got average, it means it's DC. It's a very bad DC. So instead of having a very bad DC, very ugly kind of varying DC, I would like to see my DC something like this. That would be the perfect DC. Just the voltage which does not wobble, does not alternate. It just remains constant. But this, of course, this is not constant, is it? It just keeps on changing. I can help that. I can help this by sorry. I'm just putting If I put a capacitor there, now look at this. The voltage here, oops, why is it doing this? The voltage which I had there, and past these diodes, I'm going to have it like this. Now, as the voltage goes high, so let me draw it large. As the voltage goes high, this capacitor charges. It charges to a value that much. Then it wants to discharge through this resistor. Once it's charged, once this capacitor is charged, it would like to discharge through this resistor. So it begins to discharge. It wants to discharge, and then the next pulse will arrive. Oh, this gets, I think it's getting hotter. I don't know what the problem is with the screen. Just jams. Okay. So the voltage charges the capacitor and it wants to discharge. Then can you see that it was like this before? Now, as the capacitor charges to this value, and it wants to discharge all the way back, but then because it doesn't obviously get discharged, and it only goes that far, and the next pulse will begin. And then it goes that far, and then the next pulse will begin. And then it goes that far, and the next pulse will begin. We'll come up and charge it up, and then like this. So what I will end up, in fact, if I look it on oscilloscope, it will be like that kind of thing, which is again changing DC, not constant DC, but it kind of a ripple DC. But I can decide on the value of R and C in a way that I will end up getting this much smoother. Or I can actually end up getting it really smooth, just like this. Sometimes I have to pass it through one set of filter. Filter means capacitor. Sometimes I have to do it through two filters. And I will get it to end up like a very battery-like DC voltage, which is obviously using mains. Now, using mains to convert mains into DC voltage. That is the power supply that you guys will use for your charger, for cell phone, computer, whatever. Using just the bridge rectifier. Bridge rectifier has 4 diodes, a capacitor, and whatever the load is. Any questions?
I mean, you might start going over it in a little bit, but this has to do with our ripple factor, correct? Or
yes.
Okay.
We're talking about ripple, yeah. So those changes are called ripples. Yes.
Another question I was going to ask, is there going to be like a scenario, for example, where we're going to have to solve that with values?
Yeah, of course, yes. To be given a capacitor value,
Yeah.
to be given a voltage, a peak to be, well, for example, that's what mains is. But you can use a signal generator with the certain frequency, certain peak-to-peak voltage, given a capacitor and a load, and you need to, for example, calculate what will be the peak-to-peak ripple, what would be the DC value, what would be the, everything.
Okay, thank you.
But whatever you need to know is being covered at the end of the PowerPoint 1 for this course. I've given you the full account on that.
Okay, thank you, Kasai.
And please, you can always come back to me if there's anything that you need to know. But just to put your mind at ease, I have no intention of asking any exam question on, for example, calculating the value of a capacitor to make that ripple to less than 1%, Okay. Even if you could answer that question, will you remember that in 6 months' time? That's not really going to help you in your future career. So instead of that, I could be asking, can we use mains and get it into DC voltage? That's it. Would be just one word, yes.
Thank you. Thank you for answering my question.
Yeah. Okay. In fact, in the past, I don't know, 30 odd years, an instructor asked the students, what was it? Do you know the answer to the, do you know the answer to this question? And the student answered no, and expected full grade, full mark, because he answered correctly. Like the question asked, do you know? And he said, no, I don't. Or give me the full mark. Okay. Anyway. Right, so let's continue. So that is the application of a normal, ordinary, just forward PN junction diode. Now, the same circuit again. Actually, I don't like how this is so thin. So I'm going to put the red bridge here. Oops. So there, I'm going to put a capacitor, and I'm going to put my load there. How about putting a Zener there? Well, will this Zener make sure, if for example, if I want to design an 18-volt power supply, say I need to design myself a 18-volt DC supply, that I need to have 18 volt with respect to ground at that point. I need to have 18 volt there. So based on that, I can go back and decide what this transformer needs to be. And because I know this is 120 volt RMS. If I have this voltage, I know what the peak-to-peak value is. I know what ratio transformer to choose, and I know what that voltage and that voltage, and I know exactly how much to put, and I will know by choosing these values that how I can go to 18 volt, right? That I can do. But then I don't want this 18 volt suddenly to go to 180 volt, because that would damage my load. This load is only a cell phone or a computer, say. So it requires 18 volt DC. If I apply a 180 volt DC, it's going to ruin it. I don't want that. And it's possible that mains will suddenly surge to a very, very peak value. If next door is building, for example, or if there is some kind of what do you call it? The what is it that the clouds hit each other? I mean, thunderstorm. If there is sun there, then the voltage can actually go up hugely. It can. I'm not saying it will, but it can go really high. So instead of 120 volt RMS, it can suddenly rise to 10,000 volt, for example. It can go at a very, very short period in time. It can go up to 10,000 volt. In which case, that 18 volt can also go up, say, to 200 or I don't know, something really ridiculous voltage high up. So for that reason, in order to prevent that voltage not ever to exceed 18 volt, I am going to put a Zener diode here of 18.2, for example, volt. I just go and buy myself a Zener, which is the breakdown voltage is 18.2 volt. So that the moment this voltage wants to increase beyond, much beyond 18.2 volt, it will be grounded. That is the application of Zener diode.
Mister, I got one question. I mean, in theory, this seems neat, but in practice, Zener diode like that wouldn't necessarily like protect your electronics, right? Because like, since the ranges of the lightning are probably the millions of volts, I don't think that the Zener diode will necessarily, I guess, protect everything, so to speak. Because like we observed that in real life, where in some cases, especially like if it happens relatively close, it's going to fry anything that's plugged into the mains.
Right. Actually, Israel, that's a very, very good question. Let me just come space. That's a very good question. What Israel is saying, that if that, I mean, the example I gave, it goes up to 10,000 volt, and that 18.2 volt Zener diode would ground it. What Israel is saying, what if the voltage goes up to several millions of volts? That Zener diode will melt. That's what Israel is saying. Well, the answer to that is actually no, it won't. Let's look at it. Firstly, this surge is at very, very short time, very short time. And what we are saying about Zener, don't forget that what we are saying about Zener, we are saying that once you go beyond the breakdown voltage, then this current is as much as it's necessary. It's huge. This current, there is no limit to how much this current is, and it's irrespective of the voltage. It's independent of the voltage. Increase of voltage is not going to change this current to flow anymore. Now, if the current, if the Zener diode is capable, if the junction of a Zener diode, that is the junction of the Zener diode, is capable of carrying or of tolerating this current, which is this current, how much this voltage will increase to is really not the point. And since it is at a very short period, is not going to ruin it. It's not going to harm it. I'm not saying that.
Yeah. Oh, sorry about that, Professor. So you're saying if it was for a longer period of time, it actually could fry it?
I was going to say that exactly. Because if it's the longer period, then it would melt the wires, the transformer, and everything. Then it would obviously fry, as you said, your circuit altogether. But for a surge of a very short means less than milliseconds, less than in the order of nanoseconds, that will not really harm, because the time is not sufficient for junction to get that hot. Yeah, so yes, that actually one ordinary good quality means non-Chinese. Good quality Zener diode would be good enough. Right. I have this feeling of Chinese in common with Donald Trump. No, I don't mean to disrespect anybody or any nation. I'm just making you guys laugh, that's all. Okay. So this is our power supply. Power supply is really a transformer, bridge rectifier, Zener diode, capacitor, and load. That's all. And that is the end of diode chapter. I really don't know if I have covered. I mean, let me just ask you if there is anything that you guys are still not happy and familiar with. So I don't, there is nothing else to talk about Zener, talk about the PN junction. I haven't actually said anything about all other kinds of diodes, LED diodes, photodiode, the laser diode, gun diode, tunnel diode, Schottky diode, varactor diode. What else are there? Impact diode. Let's just forget those, because those are not really part of our course. I mentioned those in the class to you guys, so that if you ever hear, you know what they are.
So the main focus is on the bridge rectifier, correct?
Absolutely. That is the most important part of the first chapter of the course, because the whole idea of learning about a diode is for us to know, for us to learn how we can design ourselves what we call power supply. Power supply means a device that you connect it to mains and receive DC voltage. And that DC voltage is sufficient, is something that we require for charges, as charges for whatever we use. TVs, radios, CD players, cell phones, everything, all electronic devices require DC input voltage. We cannot run a TV with AC. We cannot turn on radio with AC. So when those radio that we connect to mains, the mains is converted to DC and supply the radio. So there is a power supply, at the beginning of radios, TVs, cell phone, computers, you name it, everything electronic. The AC is only used in anything that rotates, like dishwashers, washing machines, AC fans, and those sort of things. Otherwise, I mean, for kettles, for example, kettles and electric cookers can be AC. They don't have to be DC, because still the element will get hot. But for TV, radio, cassette players, CD players, we cannot use AC. We have to use DC. So the fact that we put them on, connect them to mains is converted to DC first and then apply. Right. Are we ready to visit transistors now?
Yep.
Good. Okay. Transistor. Very good. Oops. This is base, this is collector, this is emitter. What this transistor does, what it does for us, if we apply a small current to the base, I'm drawing now current. I'm saying that if I apply a small current to the base, I will receive a much larger current at the collector. Now you notice that I did not use the 180 degrees out of phase and all this. I am just giving you a statement that small current through the base will give large current at the collector. That is the statement. So that it could be true about DC current. For example, 5 microamp of DC current. For example, 5 microamp of DC current to the base, at the base there, will give me, say, 5 milliamp of DC current at the collector. So this small current at the base will give me a larger current at the collector. Why does this do? So that is the statement. Now let me please listen. The transistor, its job is to receive a small current at the base and give a large current at the collector. That's what it does for us. It's called a current amplifier. That's where it's used. That's what it's for. So the very first question, that where does this transistor get energy from? How come a device like this with 3 legs, we give it a small current and it gives us large current? Where does it get the energy from? The energy comes from the bias. That is, I have to turn it on. I have to turn that transistor on and then apply small current to the base and receive large current at the collector. Okay, that's the point. So is everybody happy to this level?
Sorry. Can you say that, just that last part about how it gains that extra energy one more time?
Yeah, I have to turn it on. I have to bias it. I have to apply the right bias to the transistor. That is called turning it on. I have to turn it on so that once I bias it first, and then I apply small current to the base, then it will give me large current at the collector. Does that make sense, Isaac?
Is that from the DC that's added to it?
Exactly. So the biasing is DC, and then the signal which I applied is often AC. So, so for example, if I have a transformer, a transistor, I can connect a microphone. I mean, let me just give you a very crude circuit. Let me just give you a very kind of hypothetical circuit. If I have a transistor, I'm just giving you a circuit which will actually, it will work, but it won't work for a very long. If I just apply a battery there, and if I connect a microphone signal there, how do I apply microphone signal? I am going to just, this is microphone, okay? Here. The voltage is from a microphone. I talk to this microphone, and the voltage is applied there. That means a microphone which has two leads, one is grounded, the other one is connected there. And this transistor is turned on by this battery with respect to ground. So the battery is again like this. Can you see? This is actually exactly what we do. So I'm connecting this transistor. Yeah. Okay. I'm going to connect the transistor this way. I'm going to apply, this is VCC. This is VCC. So I don't have to write it there. And by talking through a microphone, I can hear sound there. Although, as you know, the microphone gives a very, very small signal output, but then this is quite audible. This is that minute vibration of diaphragm of microphone. If I connect the microphone direct to a loudspeaker, if I just connect this microphone direct to this loudspeaker, I won't be able to hear it. I won't be able to hear anything. But when I connect it through a transformer like this, I can hear. That means this has amplified signal for me. This is amplifier. That I want to make sure that everybody understands before I go into circuit. A transistor itself is a current amplifier. If I apply small current to the base, I will receive a larger current at the collector. Where does it get energy from? Its energy comes from its DC bias. So as you saw in that circuit, I connected this transistor to a battery with respect to ground. Then I applied a microphone here to the base, and I connected the collector through a loudspeaker, and I will be able to hear it. But if I connected just a microphone to the loudspeaker, I would not hear anything, even if I spoke to it. So this amplifies. This transistor amplifies. Now that is important for us to realize. Again, so the transistor is a device that when I apply small current, microamp of current at the base, I receive milliamp of current at the collector. Now the question is, well, that is the fundamental point about transistor. That's final, really. I mean, if you just know this, that's good. That's sufficient. Then you may ask, how does it do it? In order for me to explain to you how you can turn on a transistor by a battery and apply a small signal to the base and receive a higher signal at the collector. How does it do it? Then I will have to go into telling you about how transistor operates. Otherwise, if you didn't ask that question, that is all we need to know about transistor. A transistor is a device that when we apply small current to the base, we receive a higher current at the collector. And the energy for this amplification of current comes from the bias, comes from the DC bias.
Could you repeat that last part?
Okay, of course. So let me just do one more. If I have a transistor, and if I just bias it, that means I connect a battery. That is a battery. Then, if I apply a micro amp of current here at the base, I will receive milliamp of current there at the collector. That's what I said.
Okay, thank you. I understood that. I think I misunderstood that ending.
Right. No, so the point is that the small current to the base will give large current at the collector. Where is the energy? Where is the energy from? In order to amplify that current, small current to large current, of course, it requires energy. The energy is coming from this battery. That's all. That is really the principle of operation of a bipolar transistor. Now you may ask, how does it do it? You may ask. In order for me to explain to you how it does, I have to go to the structure of transistor for you and say transistors are manufactured this way. Emitter being highly doped, base being narrow and lightly doped, collector being even lighter doped, and then connecting two batteries. Actually, I'm going to do all this in a moment, but I'm just saying. So you ask me, how is it done? Why? Why does this transistor perform this way? That would be my answer. Why does transistor magnifies or amplifies signal? Then that would be the answer. Otherwise, if you didn't ask that, if that wasn't the issue, a transistor simply is this, that if you apply small current to the base, it will give you large current at the collector, provided you turn it on, you bias it. That's all. So principle of operation of transistor is very, very simple. Transistor is a device. We apply a small current to the base, gives a large current at the collector. Therefore, it's a current amplifier. That's all. So how does it do it? Why? Why does this do? How come it can do such magic? Because of the structure, because how it's been manufactured. It's been manufactured this way. Emitter, base, collector. That is N-type, heavily N-type. This is P-type, lighter doped than N. And this is very lightly doped. And the width of the base is narrow. So two things, manufacturers who want to make transistors have to do two things. One, make N heavily doped, P lighter doped, N very light doped, NPN, call it emitter base collector, and make the width of base narrow. That's all they have to do. Make the width of the base narrow. And then if we bias it this way, then a current will flow through, a huge current will go through because of very small current at the base. And of course, because we need to connect two batteries, we don't like to do this. This is really ugly. This is really problematic, connecting two batteries. We can actually go about using just one battery for this. Right. That structure will bring about this kind of operation. Again, two junctions, three regions, N, P, N. N is heavily doped, P is lighter doped, N again is even lighter doped. Base is pretty narrow. If we can make those, then this device will be made. And if we connect a battery there so that even a smaller voltage, this battery needs to supply to the collector and also supply smaller voltage to the base. See, we need two batteries. We need one battery there between emitter and base, which is going to be this way, between this base with respect to emitter. And then there's obviously another voltage between base and collector, which is that one. Between that voltage, sorry, that voltage and that voltage. Collector and base. Collector and base have to be reverse bias. Base emitter have to be forward bias. That has to be forward. This junction has to be forward. This has to be reverse.
Sorry, which one's forward and which one's reverse?
Emitter base is forward bias. Emitter, emitter, actually base emitter, put it this way, base emitter is forward bias. Okay, let me just do this. Hang on. This is base, this is collector, this is emitter. Collector base, reverse bias. Base emitter, forward bias.
Thanks. Got it.
Good. Honestly, without having, I mean, because this is a review, I want to make it simple. That is the operation of a transistor. A transistor is a device applying a small current to the base will give a larger current at the collector. We need to bias it in order to give us that privilege. In order for it to operate that way, we need to bias it. How do we bias? We make collector base reverse bias, base emitter forward bias. That's the end of the story. That's how transistors operate. Now, but when we bias it this way, unfortunately, we have to bias it very, very meticulously, very precisely. Now I have to bring you that ugly, ugly looking, what was it, drawing again, that I showed you earlier. This was, you know how sorry, bear with me. Is this a screen shared?
No.
No? Sorry. Okay. Of course, this is from your PowerPoint. I mean, you can obviously look at this in your own free time. I don't want to really waste your time. What I do intend showing you is this diagram. You know, because of the nature of transistor, when we apply small base, when we apply a signal to the base, that is a signal that we apply to the base. You can all see the cursor, right? This is what we apply to the base, which is in order of microamp. Base current is microamp. Then we get the correlated, related IC current in milliamp. Whatever was small current, remember, we said we small current to the base, will give a large current at the collector. Now this collector current is in milliamp, this is in microamp. Right. The fact that you can see the full signal very healthily being applied at the base, and the collector current is also all seen without chopping any piece off, because this base current was applied at the right quiescent point. Just imagine if this red signal, if I brought it down and applied, for example, from this point here, from this, and if I just applied a red from there, if I just applied it at that point, then surely this IC, the collector current, will probably be healthy that way, but the bottom part will be chopped off. The bottom of it, the bottom excursion will be chopped off. And the voltage would also move here, and some of this voltage would be chopped off. Now, do you see this?
That makes sense.
It's sure. Thank you. What I'm saying, that we have to bias it correctly. Biasing it correctly, that means deciding about that quiescent point. Really fixing a quiescent point, because we can't change the signal. The signal is given to us by the microphone. We are hoping to get a very amplified form of that signal at the collector. So we have to really make sure the biasing is meticulously done. So the quiescent point is the key issue here. Because, again, if the quiescent point, which is, see, this dotted line here, the quiescent point is, and the signal is applied on that quiescent point. It goes up and down on the quiescent point. If I chose, God forbid, I would only do that if I was a CSUN student. If I chose that Q down here, if I took my, or let's exaggerate, let's bring something like here. Just imagine if this was my quiescent point, then simply just apply this signal, this red signal, applied against this quiescent point. It will go up and down normally, but then what about the IC? The IC would be chopped off. The bottom part of this IC would be chopped off. And this part of the VCE will also be chopped off. I am not allowed to do that because this signal is not going to change anything. This is given to me. I have no control over the input signal. The input signal is given. My responsibility is just to amplify the input signal. I have no control over the input signal. All I can make sure where my quiescent point is. Quiescent point has to be picked up meticulously. Usually, the quiescent point is chosen midway on the load line. That is the safest thing to say. This is my load line, and I choose the midway, or somewhere around midway. Doesn't have to be exactly midway, but somewhere there, it would be safe. But now, if once I fix that bias, once I fix that quiescent point, I don't want that to be altered. I don't want that to be altered. Therefore, I don't want no other DC to alter this DC value for me. And that's why I have to put a capacitor at the beginning and a capacitor on bypassing the emitter resistor. That is very, very serious. That is the problem. That's the only problem with transistors. Transistors, otherwise, they operate beautifully. It's just that because deciding on the right biasing condition, on the right quiescent point, that is the difficulty with them. Right. So now I can go back. And so who honestly, who is not happy with what we just discussed?
I was gonna ask about the quiescent point, or however you pronounce it. Sorry about that.
Yeah, it is right. You're right. Quiescent point.
But yeah, that was gonna be my question. So how would you know what halfway is?
Okay. Very good. Very good question. Very good question. So I was about to say that. Quiescent point means somewhere around midway on my load line. That's the first definition. So you need to know what load line is, how we draw the load line, all that. So let me just break it into kind of steps. We need to choose this quiescent point somewhere around the midpoint on the load. This red line is called load line. This is load line. And that is somewhere midway. Look here. For example, from 0 all the way to 12, can you see the midpoint is just below the 6? That is somewhere in between. And there also from 0 milliamp to about 9 milliamp is just the midway is like 5 milliamp. It's not exactly midway, but somewhere near midway. Okay, so the quiescent point must be chosen somewhere between, in the middle of load line. That is first point. Now, how do we choose load line? Okay, load line is chosen based on the transistor, because if we don't know what transistor I'm going to use, how can I decide on the load of that transistor? So I only can draw my load line if I know what transistor I'm going to use. That means I have to look at the characteristic of a transistor. So once the characteristic of transistor is chosen, that these blue lines are the characteristic, the transistor. That is to tell me that when I apply currents of 10 milliamp, the manufacturer will give me this. The manufacturer will give me the blue characteristic. It will tell me that at 10 microamp, let's draw a line here, 10 microamp, I will get about 1 milliamp of IC current. 20 microamp, I'll get about 2 milliamp of collector current. 30 microamp, I will get about 3, and so on. So it will tell me that 80 microamp of base current will give me almost 7.7 milliamp of collector current. This manufacturer already tells me this. I have to have this characteristic. Correct? That's the step. That's the point number 1. Once I decide on once somebody has decided on the characteristic of transistor, then the next thing is, what is the VCC voltage? The VCC is the battery voltage. The examples I've always given you, is this amplifier that I'm going to design, is it going to be used for a car? In which case, the VCC is 12 volt, because cars run on 12 volt. Or is it going to be on 18 volt? I mean, somebody has to tell me what VCC is. So VCC is decided upon, and the characteristic of transistor is decided upon. And that's all I need. That's all I need. Now, let me, how about this? Oops. Sorry, just bear. Right. So as you saw, obviously the characteristic here, the characteristic is plotted what? This is IC in milliamp.
Dr. Kasai?
Yeah, sure.
Oh, we can't see your screen.
Oh, I'm sorry. I'm very sorry. I'm sorry again. Yeah, just a minute. Sorry about that. Oh dear, this screen gets locked. Okay, so this is the characteristic of transistor. This is given to me by the manufacturer. This is IC in milliamp. This is VCE, VCE in volt, of course. Now, I need to know what VCC is. VCC must be given to me. Is the battery of my circuit. So, if, for example, if VCC is, for example, 15 volt, and if this RC, the load is, say, 1K, I'm just making these simple nominal, but I actually say call it 5K, just 5K. Now, the characteristic tells me midway should be somewhere, I don't know, call it 6 volt. I mean, I'm just making, as I said, somewhere here between 0 and VCE, say 6 volts. I don't know, but I have to look it up. I'm just saying the characteristic will tell me this somewhere in between, midway, 6 volt. That means the VCE voltage, this is 6 volt. If there is 6 volt there, 15 volt there, that means 9 volt in this transistor. This resistor, I'm sorry, 9 volt. See, 15 volt, 6 volt, that means 9 volt there. Okay, so if it's 9 volt, V equal IR, that's 5K times I. I will be 9 over 5, which is 2. It's not 2, is it? say it's 1.9, something like that. Actually, come on. 1.2 is it? 1.2 milliamp. Right. So the IC current, this is IC. See, the current that flows here has to be 1.2 milliamp. Now I have IC, I have RC, I have VCC. So I can say VCC equal IC RC plus VCE. I'm just making too much mess here. I'm sorry about this. Let me write it down. VCC equal IC RC plus VCE. Can you see that? VCC, that is this voltage with respect to ground. The whole voltage is this amount of voltage, VCE, plus ICRC, which is that much. That much. That voltage is that voltage. Okay. How do I I see. My load line is like this. Only the two end of my load line is where here at this point IC is equal 0. IC is equal 0. At this point VCE is equal 0. So in that relationship, VCC is equal VCE plus IC RC. Once I can say IC equals 0, and then VCC will be VCE. I choose this value here. I call it 15 volt. And then I say VCE is equal 0, in which case IC will be VCC over RC, which is 15 divided by 5K, which is 3 milliamp. And that would be IC 3 milliamp. Do you see that? So I can now draw my load line. And now I go and say, I like that point to be my quiescent point. And therefore, I begin the whole thing again. How are we?
Good.
Very good. Right, so I need to choose my quiescent point. Once I choose the quiescent point, that I know how much voltage to be dropped on the VCE and what is going to be my IC, I can decide on the value of the components now. So because I want to use one battery, so now I'm pretty good actually. I'm doing very well. I can now decide on my amplifier this way. Why is not getting any bigger? I don't know what's happening here. Maybe the battery is running low. Never mind. Oh, I can use this red one actually. Oops. Okay. So VCC actually I'm making it, let's make it a bit smaller. Come on, for God's sake. Oh, oh, I know what's happening. Right, that's better. You see, this resistor is I need because it's my load. This is VCC. Now this resistor I also need because if I don't put a resistor there, my transistor will burn out. My transistor will not last very long. I need to put a resistor here to save the transistor. And in order to use one battery, I can use two resistors here, like R1 and R2. In order to use just one battery, one VCC, to bias both the collector base, that would be reverse bias. That means this voltage at collector must be much bigger than the base voltage for this to be reverse bias. And base emitter must be forward bias. That voltage at the base must be higher than the emitter voltage. So I put two resistors here, two resistors there. Then in order to complete my amplifier, I need to put a capacitor there. I need to put a capacitor there. And I need to put a capacitor there. And that is ground. That is my amplifier. So now, by choosing the right R2, R1, RC, and RE, and CE, and CO, and CC, by choosing, and the transistor actually, by choosing all these components right, then I can apply a signal there, and I can receive a signal there. Do you follow what I'm saying? So I will use this circuit. This circuit is a transistor, a battery, 4 resistors, and 3 capacitors. If I choose each value, the right value, then I can honestly say that if I apply a small signal to the base, I will receive a large signal at the collector. So let me stop the share and ask if everybody is happy and everybody follows what we are saying. See, so if, for example, if I was going to ask an exam question, I'm just giving you an example. I could say, design an amplifier. Well, when I say design an amplifier, you have to have this circuit in mind. That is the amplifier, because each component is necessary. So if you remember in the assignment, or was it, I don't know where I gave you, did we have a midterm? Did we not have a midterm?
No, but you did give an assignment to design an amplifier.
Exactly right. So that's correct. So when I say design an audio amplifier, then I said, imagine you've looked it up online, and that is the circuit that you thought this is the circuit you will be using, because that is the amplifier. Your job would be to determine the values of all these components, which we are going to do now. Now, because why do we have to choose them meticulously? Now, I want you to honestly agree with me that we can't just say, oh, let's put a resistor here and a resistor there and just see what happens. It won't work unless we do it precisely and very accurately. Unfortunately, that is the problem with bipolar transistors. We have to be very, very precise. Otherwise, our amplifier will not be amplifying distortionlessly. For our amplifier to amplify with no distortion, we have to do it very, very meticulously, very precisely. So those values have to be specifically chosen. Right. Are we happy so far? Are we all good? Do we all follow? Any questions at all? So I'm about to tell you about how we choose the values of these components. Good. Thank you very much. Right. The very first thing is to choose the right transistor. How do I choose the right transistor? Well, I'll go for the, I don't know, common transistor like 2N, 2N, 2, 2, 2, 2 is the most normal used transistor, or BC107. These are famous. These are famous transistors. Just anything like that would do. So I choose a transistor. Obviously, I need to look up the characteristic and look up the everything. And then I need to choose about the values. Now, before I do this, if you remember, I went and I urge you to go and look in and listen to that lecture when we said why, how did we arrive at this circuit. Let me just quickly remind you that I went about biasing transistor with applying a voltage there, call it VEE. And then this was the base, this was base, this was positive, and that was negative. Then we brought this battery and connected it up there. I'm just reminding you, I'm not going into that anymore because we don't have time. So I brought that up here. And then I said this can be the 7-in voltage. If it is 7-in, there has to be a R7 there. And because we didn't have a resistor there before, this R7 must be as low as possible or negligible. And by proving, in order to make this negligible, we arrived at this conclusion that RB must be much less than 1 plus beta RE. That is what we arrived based on that. I don't expect you to do that proving. It doesn't really matter, but for you to understand why should RB be much less than 1 plus beta RE. In order to prove this, in order to see why, we went and proved that thing. So please go back to that lecture that we discussed this in some detail. Let me make sure everybody's good with that. Do you follow what I'm saying? So there was a lecture that we actually showed how to bias transistor, and one way of biasing transistor, because we wanted base to be positive with respect to emitter. So we, instead of doing this, we grounded base and we applied the negative voltage to the emitter. And then we brought it up, and then we went to R7-in, V7-in, and chose the RB and blah, blah, blah to the end. Please go and look that up. And the reason we did all that, to show that RB being R1, R2 in parallel. RB means R1, R2 parallel, which I will go into that in a moment. The total of those, the combination of those two resistors must be a lot less than 1 plus beta RE. Right. That's a very, very big hint. So this R1, R2, now RB that we just said is equal R1 parallel R2. RB must be a lot less, much smaller than 1 plus beta RE. That is something that we can rely on. That we know. Okay. So right. So our job now is to choose all these values, RC, RE, whether you call it R1 or it doesn't matter really, R1, R2, call this C in, call this CE, and we call that CO. And this is VCC. Right. In order to decide about all these, somebody has to tell us what VCC is. We are just going to say VCC is 12 volt. That somebody has to tell us. You can't just guess everything. somebody has to tell us what our load is and say, for example, RC, call it 4K. If we are giving these two, we can do the rest. We can decide on the rest. But then the transistor that we use, we know the beta. The beta value is given by the what do you call it? The data sheet of transistor. And normally, let's call this just 199. The reason we call beta 199, because then alpha would be 0.995. If beta is 199, we can calculate alpha to be 0.999. So these are our knowns. Okay, let's begin. I'm sure that now you see that everybody can decide on values of RE, R1, R2, and all that. Right. If there's 12 volt here, 12 volt. Oh, okay. Before I go, do you see the question now? The question is, we want to design an amplifier that is to decide about the values of all these components. We said somebody has to tell us what the VCC is, because that's the battery that we're going to use. We have to also, they have to tell us what is the load, because the load of this amplifier, is it, for example, yet another amplifier? See, that amplifier could be a pre-stage amplifier for yet another stage of amplifier. That would be our load. Or is our load going to be loudspeaker? Or is our load going to be another circuit? So we are amplifying a signal for a different circuit. So depending on what our load is, somebody has to tell us. We don't know what we are designing for. So somebody has to tell us what the load is. That load we are going to show in the form of RC for now. We said, say 4K. So the battery is known, RC is known. Okay. Then VCC is known, RC is known. The transistor we looked up, and the beta value is 199. Okay. So now, how do we choose about the value of RE? So for now, we are not going to do the capacitors yet. We are going to decide about RC, R1, R2, RE. RC is already known. Then we said we go about somehow deciding about the value of RE, and then R2 and R1. So if, for example, the VCC is 12 volt, how much do I want VCE to be? That means this voltage from there to there. How much do I want that VCE to be? Usually, I want almost half of this voltage, VCC. I want VCE to be halfway between that and that. I am going to call VCE for now 5 volt. I mean, I don't want to make it exactly 6 volt for you not to learn that it has to be exact. But for 5 volt across VCE, I'm pretty safe. It's somewhere in between. So if that is 5 volt, then the remaining 12 minus 5, which is 7 volts, this 7 volt is going to be that voltage, which is IC RC. And this voltage, the total of these two, IE RE. So I can say IC RC plus IE RE is 7 volt. That I can say. But then I know that IC is almost equal IE, because I know that IC is alpha IE, and alpha is 0.995. So really, IC is almost equal IE. All right. So now life becomes simpler. How about 7 volt is equal I or IC RE plus RC. That means RC plus RE is equal 7 divided by IC. And if, I'm just making a big if, then I'll come back to this if. For now, if I make IC 1 milliamp, then RC plus RE is going to be 7 kilo ohm. In which case, since my RC was 4K, then RE is to be 3K. So now RE is 3K. Now, please remember, I made a precondition here for choosing RE3K. Do I need to pause, or is everybody good?
Well, I guess kind of obvious question. Again, that's precondition is just primarily from experience, right? That you could safely assume that it is 1 milliamp, because it seems like we do that in a lot of the examples that we do.
Actually, you're right, and yet I need to, yes, you're right. So what you said about based on experience, it's based on 2 kinds of experience. One experience, one thing that I do know, that RE must be small in comparison to RC. Because the bigger RE, the more trouble I have, the more loss I have. I like to make my RE as small as possible. And yet, obviously, there is a limit to how much I can go to small. So RE has to be small, smaller than RC. Now, this is one point. And the next point, that IE, which this is something that I have not spoken about this semester, we will speak about next semester. The value of IE is that value that ultimately determined your voltage gain of the amplifier. The voltage gain, which we call him GM, we call that transconductance. Don't worry about this, I'm just saying it. G suffix M is known as the voltage amplification of an amplifier, transconductance. That is, what is it? Is a small RE divided by big IE. So here, the IE is going to play a major role. We normally, if we choose IE to be around 1 milliamp, we are safe. We're good. So it's 2 experiences. One, we want RE to be small, because don't forget, we are now designing based on trial and error. We are just designing. In any design, we have to go about things this way. We just do it and then make corrections as we go along. This is what we do in any design. So because we know we want IE later on to be around 1 milliamp because of our GM or transconductance, which is not really our concern right now, but we also want RE. RE needs to be small because RE is not doing me any favor. RE is only saving the transistor. Why do I want that RE to be big? If I can get away with a small RE, that's well and good. So these are, yes.